Okay, so we got another review for a test. So we're gonna move the camera over first. We're gonna do a guided practice going through each and every question so you're able to check your answers. All right, look at number one. A block slides down a frictionless ramp. The angle of the ramp is 27 degrees. Determine the acceleration down the ramp. Bleh. So specifically when we're looking at a frictionless ramp with no additional applied forces, we do have a working equation we can go straight into where the acceleration equals your gravity times the sine of your angle. Okay, so in this one we've got all that information. Gravity 9.8 times the sine of an angle of 27 degrees. So 9.8 sine 27, we've got an acceleration of 4.45 meters per second squared. One bit of answer checking when you're finding acceleration. If you ever end up with a number for acceleration larger than 9.8 for something sliding down a ramp, it means you screwed up somewhere along the way, because this is just a component of gravity. It will never be larger than gravity itself. All right, so that is number one. Number two, block slides down a frictionless ramp, which is 6 meters long and 2.5 meters high. The block starts from rest at the top of the ramp and slides all the way down the ramp. Determine the angle of the ramp. So we've got a length of 6 meters, we've got a height of 2.5, and we're looking for that angle at the base. So we've got our hypotenuse and we've got our opposite side. So since we're looking for that angle there, sine of our angle equals opposite over hypotenuse. So that is going to be, to get our angle, the inverse sine of our opposite side divided by our hypotenuse. We end up with an angle of 24.6 degrees. Okay, so there's 2A. For B, use the acceleration down the ramp and the length of the ramp to determine the speed of the block as it reaches the bottom of the ramp. Now, we are looking at a frictionless ramp again, so we can find our acceleration as easily as doing 9.8 times the sine of our angle, which just gives us an acceleration of 4.08 meters per second squared. And the other information that we have, we've got the distance down the ramp, which is 6 meters. We've got an initial velocity of 0 meters per second because it is starting from rest. All right, so now if we're looking for our final velocity, the formula that we've got that involves all of those is formula C, which is Vf squared equals Vi squared plus 2Ax. Solving that for your final velocity will just be the square root of Vi squared plus 2Ax. Plugging in our numbers, we've got our initial velocity of 0 squared plus 2 times, not 9.8, 4.08 times our distance of 6. Okay, so square root of 2 times our answer from the previous question times 6. And wow, that's a nice, pretty number. We end up with a final velocity of 7 meters per second. Okay, now C is showing off an interesting thing that happens for frictionless ramps. Assume the block was dropped off the back of the ramp instead, free falling for 2.5 meters. What would its final velocity be as it reaches the ground? So in that case, because it's in free fall, its acceleration would be 9.8 meters per second squared. Its distance that it's traveling is 2.5 meters. And again, its initial velocity is 0 meters per second. Since we're looking for the same thing we were in the other problem, just with different numbers, we're using the same formula. So our final velocity will be equal to the square root of our initial speed squared plus 2 times our acceleration times the distance. Okay, so we've got square root of 2 times 9.8 times 2.5. And again, that gives us 7. So when you've got a frictionless ramp with no additional forces, it will reach the same speed if it's going down the ramp as it does falling off the ramp, simply because it's split into components that are along the same angles, right? If it's allowed to accelerate in the direction of gravity over that shorter distance, it will end up reaching the same speed as if it goes down a side at the same angle as the parallel component. All right, longer distance, less acceleration, shorter distance, more acceleration. It's called path independence. No matter what path it takes down this frictionless ramp, it will end up reaching the same final speed. Okay, so look at number 3. Usually when we're drawing these vectors, we're talking about forces. This one is specifically asking about components of our gravity. Okay, so if we're looking at our forces on here, all right, specifically just the components of our weight. Okay, our parallel component is just the weight. Actually, I'm going to switch that out with mass times gravity times the sine of our angle. Our perpendicular is just equal to mass times gravity times the cosine of our angle. Okay, if we're looking for the acceleration in those directions, well, they follow the exact same direction as our force vectors do, right? If we think about F equals ma, whatever direction our force is in, our acceleration will also be in the same direction. So if instead we look at a triangle that has acceleration, so gravity pulling it down, and a perpendicular gravitational component, and a parallel gravitational component, they're going to be at the exact same proportion in the exact same directions as our forces are. All right, so still using sine for your parallel component and cosine for your perpendicular component. The difference is we're just looking at acceleration, right? Using Newton's second law, force divided by mass is equal to your acceleration. So if we just take these formulas for our forces and divide them by mass, that will give us formulas for the components of our gravity. Okay, so for number 3, where it's asking about at what angle will the parallel component of g equal 4.9 meters per second squared, that's telling us to use that right there. Okay, so we've got 4.9 for our parallel component equals g times the sine of our angle. We're looking for theta, so we're going to divide over 9.8, so 4.9 divided by 9.8, and then we're looking for theta, so we're going to take the inverse sine of that, which gives us an angle of 30 degrees. Okay, for the next one, it's telling us that our perpendicular component is 4.9 this time. So, right, so looking at our perpendicular, so 4.9 for our perpendicular component, 9.8 for gravity, and instead of sine, we have cosine. Okay, so 4.9 divided by 9.8. All right, then we take the inverse cosine of that, and we end up getting 60 degrees instead. Okay, so when it starts talking about components of gravity, it's the exact same triangle, you're just getting rid of mass. All right, number 4, sorry, my pen was a little bit too far out. Number 4, a 6 kilogram block starts sliding from rest and slides down a frictionless ramp. The length of the ramp is 4 meters. The angle of the ramp is 40 degrees. Determine the, and we're looking at a few things. So mass of the block is told to us, it's 6 kilograms. Weight of the block, well, that would be mass times gravity. So that would be 6 times 9.8. So we end up with 58.8 newtons. All right. C, parallel component of our weight. So that would be F parallel equals FW times the sine of our angle. All right. So we've already got the weight in there. So we're going to multiply that by the sine of our angle, which was 40 degrees. And we end up with a parallel component of 37.8 newtons. Okay. Now D, our perpendicular component, is our weight times the cosine of our angle. Okay, so our weight of 58.8 times the cosine of 40. All right, so that gives us 45.0 newtons. All right, next one, we're looking for the height of the ramp. Okay, so we've got some dimensions here. All right, we're told that the ramp is 4 meters long, and we've got an angle of 40 degrees. We're looking for that height over there. Okay, so we've got our hypotenuse, we've got our angle, and we're looking for that opposite side. So we're going to be using sine of our angle equals opposite over our hypotenuse. Just going to multiply that over. So that would be 4 times the sine of our angle, which is 40, giving us a height of this ramp of 2.57 meters. Okay. Now, when we're looking at F, we have options, all right, because this is a frictionless ramp, which means that we can use path independence. We could just drop an object off of the end of it, or we could let it slide down. Ultimately, we'll end up reaching the exact same final velocity. Okay. Let's use just dropping it off the ramp, because that way we don't need to worry about finding acceleration. We'll already know it. All right, so our acceleration is just going to equal 9.8. The distance that it's falling, we're just dropping it off the ramp, 2.57, and its initial speed is 0. All right, so again, looking for our final velocity is going to be equal to 0 squared plus 2 times our acceleration times our distance of 2.57. Okay, now you could absolutely use the numbers from the ramp itself by figuring out what your acceleration is down the ramp, and then using the length of the ramp as your distance. You'll still end up with the exact same number of 7.10 meters per second at the end of the ramp. Okay, so that is us through 4. Let's continue on. All right, number 5. A 5 kilogram block slides down the ramp. The ramp is 6 meters long and 2.5 meters high, so that is the same dimensions as we had up there. So real quick, that is going to be 24.6 degrees. Just going to write that on here so that we can have that for later. So it's sliding down that ramp. Coefficient of friction is 0.244. Determine the, and we're looking for mass of the block, weight of the block, parallel component of the weight, perpendicular component of the weight, normal force, friction force, net force, acceleration, and speed of the block when it reaches the bottom of the ramp. All right, so 5. A, mass of the block told to us, 5 kilograms. Done. B, that's a B, that's a B. B, weight of the block, well, that's 5 times 9.8, which I've done 5 million times recently. It's just going to be 49 newtons. All right, C, looking for the parallel component of the weight, that would be our weight, times the, oh my god, sine of our angle equals our parallel component. Okay, so that would be 49 times the sine of 24.6. Okay, so that gives us a parallel component of 20.4 newtons. All right, and D, perpendicular component. The light just turned off, but I think it's still bright enough on video. Yeah, that'll work. All right, perpendicular component. Now we're looking at our weight times the cosine of our angle. Okay, so that'll be 49 times the cosine of 24.6, which gives us a perpendicular component of 44.6 newtons. All right, now E, looking for our normal force when we're looking at these blocks sliding down stuff. All right, the perpendicular component will always end up balancing out with the normal force. The force into the block will be the same as the force back out of it. So that means that our perpendicular component will be our normal force as well. All right, you could put a negative on there, but you really don't need to worry about direction when you're looking at net force when things are canceling each other out. I'm just putting the magnitude of each of these forces. F, friction force. Okay. It tells us our coefficient of friction is 0.244. All right, so our formula we have for friction is coefficient of friction times our normal force. We already have our normal force, so we can just plug and chug. All right, so we're going to take 0.244, the coefficient of friction that it told us, and multiply that by our normal force. So 0.244 times 44.6. Okay, and we end up getting 10.9 newtons. There we go. All right, so now when we're looking for our net force, real quick, I'm going to add that friction force onto our diagram. Okay, we're looking for our net force. If we're looking at the forces on this object, the perpendicular component and the normal force are the exact same size but in opposite directions. So those two will cancel out. So what we're left with is the friction and our parallel force. All right, so ultimately when we're looking for our net force, two of our forces go away. And then the other two, whatever's left over, will be your net force. Okay? One of them will be in the positive direction, one of them will be in the negative direction. Since this thing is moving down the ramp, let's say that down the ramp is positive and up the ramp is negative. All right, so our net force is just going to be negative our friction plus our parallel component, the 20.4. Okay? So basically it's just going to be the difference of these two. All right, and we end up getting 9.52 newtons. All right, and that's going to be in the same sign as the larger force. All right, so going down the ramp. All right, and that is G. Now for acceleration, we've got F equals ma. All right, so moving that around to solve for acceleration, we can just take our net force and divide by our mass. Okay, so net force 9.52, our mass of 5 kilograms. So just dividing that by 5, and that gives us an acceleration of 1.90 meters per second squared. Okay. Final one. Looking for the speed of the block when it reaches the bottom of the ramp. Again, we know initial velocity, distance traveled, acceleration. We're looking for final velocity. So again, we're using VF equals square root of VI squared plus 2AX. Plug in our stuff. Initial speed of 0 squared plus 2 times our acceleration of 1.9 times our distance of, how long is this ramp? 6 meters. There we go. So 2 times our answer times 6. And then taking the square root of all that, we end up with a final velocity of 4.78 meters per second. Okay. So that's it for 5. That took a lot of space. All right, number 6. A 10 kilogram block slides down a 37-degree ramp. Coefficient of friction is 0.3. Determine the normal force, friction force, and net force. All right, so our normal force, that's just going to be the same thing as our perpendicular component, which is our weight times the cosine of our angle, which is just mass times gravity times the cosine of our angle. Let's plug in our numbers. We've got a mass of 10, we've got a gravity of 9.8, and then cosine of 37. All right, so 98 times the cosine of 37, and that gives us a normal force of 78.3 newtons. Okay. Looking for our friction force, we have our mu, our coefficient of friction, so we can just plug and chug into our basic friction equation. And we got 0.3 times our normal force of 78.3. All right, so we're just going to multiply that by 0.3, and we end up with a friction force of 23.5 newtons. All right, and then C, looking for our net force. For this one, let's think about what forces are acting on this. Okay, so we've got our weight, which we split up into two components. We've got our perpendicular, we've got our parallel, we've got our normal, and we've got our friction force. Okay, when we're looking for our net force, that's the sum of all of the forces on this object. So we've got our normal, we've got our perpendicular, we've got our parallel, we've got our friction. These two always cancel out, so what we're left with to find our net force is our parallel and our friction force. Now we have already found our friction force, we are going to need to find our parallel. Okay, so we're just going to substitute in what that ends up equaling. All right, so F net is going to be equal to mass times gravity times the sine of our angle minus our friction force of 23.5 because it's in the opposite direction. Okay, so we've got 98 times the sine of our angle of 37 minus our friction force. All right, and that ends up giving us a net force of 35.5 newtons. Okay, and that's it for number 6. I'm going to get rid of this sheet, and we're going to start up on the next one. We've got number 7. All right, so this one, a 10 kilogram block slides down a 30-degree ramp at a constant speed. Determine the parallel component of the weight. All right, so parallel component is your weight times the sine of the angle it's at. All right, so the weight of this thing, that's mass times gravity. We've got a mass of 10 kilograms, so that makes a nice pretty weight for us. It's just going to be 98 times the sine of our angle, which is 30. All right, so 98 sine 30. That gives us a parallel component of 49 newtons. Okay, and then B, looking for the friction force. Now this does tell us one very important piece of information, that is that it's going at a constant speed. Okay, that means that all of our forces have balanced out. We can go back to the diagram we had from the last one, where we had all those on here. Okay, so if your net force is 0, that means that all your forces pointing down the ramp need to be equal to all your forces pointing up the ramp. In this case, the only forces we have up and down the ramp are our parallel component and our friction force. Okay, so if this thing is moving at a constant speed, because we don't have any additional forces, that means that our parallel component needs to be canceling out with the force opposing its motion. In other words, needs to be the same force as your friction. Your friction will also need to be 49. Okay, perpendicular component of the weight. Okay, that one is just going to be our weight times the cosine of our angle. All right, so that'll be 98 cosine 30. All right, so that ends up giving us a perpendicular component of 85 newtons, 84.9. What am I doing? I'm getting rid of a sig fig for some reason. All right, so 84.9. Again, because this thing has a net force of 0, that means that the perpendicular component will need to balance out with the normal force. So for D, our normal force will also be 84.9 newtons. All right, for E, looking for our coefficient of friction, the formula has that is FF equals mu times Fn. Moving it around, mu will be equal to our friction force divided by our normal force, plugging in our numbers. Our friction force was 49, our normal force 84.9. And there we go. So we end up with a coefficient of friction of 0.577. Okay, no units on that. Coefficient of friction is a ratio. It has no units of its own. All right, number 8. Okay, so this one's telling us that we've got a 5 kilogram block sliding down a ramp at 30 degrees at a constant speed, determining the coefficient of friction. Now, there is a trick that I want to teach you that might make things faster. Okay, these two ramps, they have different masses down them. All right, 10 kilograms versus 5 kilograms, but other than that, they are the same. You have a 30-degree angle, and you're going at a constant speed. Okay, so for this very particular case, all right, so when F net equals 0 and no additional applied force, mu becomes easier to find. Okay, so let's think about what was acting on this thing. All right, if we're looking at our friction equation. Okay, when you don't have additional forces, it's just gravity, friction, and your normal force. Your friction force will just be equal to your parallel force. All right, and our normal force is always going to be equal to our perpendicular component. Okay, now remember, this is only when F net is 0 and you have no applied force. You cannot use what we're going to end up getting in every situation. This is specifically for a ramp that has friction and you are going at a constant speed and there are no additional applied forces. All right. So when we think about F parallel, okay, that is your weight times the sine of your angle. All right. Your perpendicular is your weight times the cosine of your angle. Okay, and then solving this thing for mu, moving it around, that would be FW sine theta divided by FW cosine theta. Okay, well, we've got weight on top and bottom, so weight cancels out, and sine theta divided by cosine theta, that's a trig identity. The sine of an angle divided by the cosine of an angle is equal to the tangent of an angle. So when your F net is 0 and you have no additional applied forces, you can find your coefficient of friction as easily as just taking the tangent of your angle. This is a very specific case. Do not use it in general. Use it only when you're lazy and you have this specific scenario, when it's going at constant speed and you have no applied force. Okay, so it's just going to be the tangent of 30. All right, so this is what we ended up getting for a coefficient of friction for the other ramp that was going at a constant speed, had the same angle, it just had a different mass. It should end up giving us the exact same answer. So tangent of 30, hey, look at that. It gives us the exact same answer all the way down. All right, so we end up with the exact same answer for this because it is a very specific situation. When your F net is equal to 0, you're going at constant speed, and you have no applied force, things will cancel out finding your mu. All right? Do not use it for every case. This is specifically for this case. All right? So there is number 8. Let's look at number 9. On number 9, we've got a 5 kilogram block, so already looking at A, looking for the weight, it's going to be 49 newtons. We've done that enough times. and is resting on the ground. The ground is flat. Determine V. All right, so if it's just resting on the ground, that means that the ground will be applying the same force upward that your weight is pointing downwards with. So that would be 49 newtons for B as well. As long as you're not looking at a slant, those should, in general, be equivalent unless you've got additional upward and downward forces, like we have in the rest of it. So a normal force on the block if an additional force of 10 newtons is applied downward. So if we've got our block, we've got 49 newtons going down. We're applying an additional 10 newtons down. Total, this thing isn't moving through the ground. So that means that our normal force, whatever it happens to be, happens to cancel out both of those forces together. All right, so two forces together would be 59 newtons. That means that our normal force also needs to be 59 newtons. Okay, looking at D, normal force on the ground if 10 newtons is applied upward. So in this case, we've still got our 49 newtons going down. We've got 10 newtons going up, and whatever our Fn needs to be. Now this thing isn't moving up or down. That means that these three forces have to cancel out. We've got 49 down. That means we need a total of 49 going up. 10 of it is already accounted for. So what does our normal force have to be? Well, that would be 39 newtons. Okay. E. All right, now we've got a force being applied at an angle. So we've got our weight going down of 49 newtons. We've got a force of 10 newtons being applied at 30 degrees downward. All right, so when we're talking about up and down, it's being measured from the horizontal. Okay, so we've got an angle of 30 degrees right here. Our hypotenuse is 10 newtons, and we've got a normal force going up this way. Now, we don't really care about what the side-to-side force is. We only care about what happens to our normal force, so we need to know what's happening up and down. All right, so up and down, we've got some unknown force going up that we're looking for, and we've got this downward side, all right, our gravity, plus whatever this side of this triangle happens to be. So we need to find this side of our triangle and add that to our weight to figure out what our normal force is. Okay, so we've got an angle, we've got a hypotenuse, we're looking for that opposite side. That means we're using sine. Sine of our angle equals opposite over hypotenuse. We're looking for O. So we're just going to multiply our hypotenuse over. And that opposite side equals our hypotenuse times sine of our angle. All right, so our hypotenuse, we've got 10 times the sine of our angle, which is 30. All right, so that's giving us 5. We're just going to add that to the weight because both of those forces are pointing downward. We've got a total of 54 newtons pointing downward. That means we need a total of 54 newtons pointing upward to cancel it out. All right, F. Normal force on the block if a force of 10 newtons is applied at a 25-degree angle upward. Okay, so instead of pointing down, our angle is now pointing up. So 25 degrees there, 10 newtons, some unknown Fn. Okay, so our total downward force needs to equal our total upward force. We've got some unknown Fn, and we've got this side of this triangle pointing up. All right, so we need to figure out what that side of the triangle is. Again, we're looking at the opposite side, so we're going to be using sine again. In this case, the only thing that's changing is the angle. All right, so 10 sine 25, that gives us an upward component over here of 4.23. All right, this is already canceling out some of our weight, so let's see what's left of our weight after that cancels it out. All right, so I'm taking this upward component, I'm subtracting it from the weight to figure out what the normal force has to cancel out. We end up with 44.8 newtons. All right, and for all of these, you could just look at F net equals the sum of all your forces, so your weight plus your normal plus any vertical components of your applied force, and just keep track of what directions things are going. All right, if you say weight is downward, make sure that your normal force is the opposite sign, and then your applied force, well, that depends on which direction it's going as to which sign you make it. All right, and for all of these, your F net up and down would end up being 0 because it's not accelerating in that direction. Okay, number 10, it is accelerating up and down. So, on number 10, Sasha, who has a mass of 54 kilograms, is chilling in an elevator again. She really likes elevators. Her family is starting to get worried. Seriously, it's starting to be a problem. She's just living in elevators and shouting squatters' rights at anyone who comes in. When the elevator is accelerating upward, all right, so we're looking for some stuff. All right, so we've got A, I. When it's accelerating upward, it takes 5 seconds for the elevator to go from rest to 15 meters per second. What is the elevator's acceleration? Now that is a kinematics problem. All right, so A equals VF minus VI over T. All right, so we've got a final velocity of 15 meters per second, initial velocity of 0, a time of 5 seconds. 15 over 5, it is 3 meters per second squared for our acceleration. All right, for II, we're looking for the net force. All right, so for each of these, we're looking for net force. We can just use F net equals mass times acceleration because we happen to know both. So 54 times our acceleration of 3, we end up with a net force of 162 newtons. Okay, next bit, we're looking for the total upward force. All right, let's think about that definition of net force. All right, it's equal to the sum of all the forces on an object. The two forces that we've got are the upward force from our normal force and her weight. Okay, we know that she has a net force of 162. We already found that. Okay, we don't know what Fn is. Fw we can find pretty quickly. That's just her mass times acceleration. So 9.8 times her mass of 54. All right, so she has a weight of 529. Okay, now we do need to pay attention to directions. She is accelerating upward, so her net force should be a different sign than her weight, which is pointing downwards. Let's say weight is negative. Okay, so now looking for our normal force, we've got 162, and we're just going to be adding that 529 over to get our normal force. So we end up with 691 newtons of force upward on her at the beginning for A. All right, now B happens to be a little bit easier because this thing is moving at a constant rate. So anytime you've got something moving at a constant rate, your net force equals 0. And we're done. No math required. All your forces have canceled out if you're moving at a constant speed. All right, also if you're moving at constant speed, well, your speed isn't changing, which means your acceleration is also 0. Okay, all right, so looking at our total upward force, we can again look at our F net equals Fn plus Fw. Okay, our net force is 0, our Fn is unknown, and our weight is still that negative 529 because it's pointing downwards. So to get to our Fn, we just add that over. Our Fn ends up equaling 529 newtons. Our normal force and our weight are equivalent because our net force is 0 in this case. Okay. All right, looking at C. Oh, I'm running out of paper. All right, so C, I. It says that the elevator takes 3 seconds to go from rest to negative 15 meters per second, so it is implying that the direction of downward is negative in this one. So let's just keep the direction scheme that this one has. What is the elevator's acceleration? All right, so acceleration, we've got our final velocity of negative 15 minus our initial velocity of 0 over a time of 3 seconds, so 15 over 3. This ends up giving us an acceleration of negative 5 meters per second squared. Okay, for part 2, what is the net force on Sasha? Again, we can do F net equals mass times acceleration, so 54 times our acceleration of negative 5. All right, so in this case, we've got a net force of 270 newtons. And remember in this one, it said that down was negative, so this force is going downward, which will be important in the next bit. Okay, and now looking for our total upward force, our normal force. We've got the exact same definition from earlier. Our F net is equal to the sum of our two forces that we've got acting on her, the normal force and her weight. All right, her net force, negative 270, saying that up is positive, down is negative. Fn, we don't know. And then her weight is still the same from earlier, which was the 529. Weight is still pointing downward, so we're going to leave that as a negative number as well. Okay, so now to get to the Fw, we would just add that over. So negative 270 plus 529. There we go. We end up with 259 newtons. Okay, so you'll notice that we have a larger normal force when she is accelerating upward than we do when she's accelerating downward, simply because you need a larger upward force to accelerate up. All right, so that is it for number 10. Last one, number 11. Let's get some nice clean paper. All right, so Boris is mowing his lawn. The grass has a coefficient of friction of 0.2. His lawnmower has a mass of 30 kilograms. The force applied to the mower is at 40 degrees from horizontal. Okay, so let's draw our diagram first because that will be helpful. All right, so we've got a weight pointing downward. We've got an applied force pushing forward and down on our lawnmower. All right, so we got 40 degrees there. One piece of information that we do need on this, which should be on yours on Schoology, is that our applied force is 100 newtons. So 100 is our hypotenuse here. It would be unsolvable without that. The other thing that we've got is a normal force upward and a friction force opposing motion in the opposite direction of its motion. Okay, so we've got a vector diagram, obviously not to scale, but you know, it'll work. Looking for our other stuff. Weight of the lawnmower. We've got a mass of 30 kilograms, so looking for our weight, that's just going to be mass times gravity. So our mass is 30, gravity 9.8. All right, and we end up with a weight of 294 newtons. Okay, we're looking for the downward component of the applied force. Okay, so that is this side of that triangle. We've got an angle, we've got a hypotenuse, and we're looking for our opposite side. So we're going to be using the sine. Sine of our angle equals opposite over hypotenuse. Looking for our opposite side, that's going to be a hypotenuse of 100 multiplied by the sine of our angle, sine of 40. All right, so 100 sine 40. That gives us an opposite side of 64.3 newtons. All right, now D, looking for the horizontal component. So we already found the opposite side, looking for our adjacent side instead of sine. Now we're looking at cosine. So cosine of our angle equals adjacent over hypotenuse. All right, so adjacent is going to be equal to our hypotenuse times the cosine of our angle, which is 40. So 100 cosine 40. That gives us a horizontal force of 76.6 newtons. All right. So now looking for E, determine our normal force. All right. Our normal force is the upward force that is canceling out these two forces here. Okay. So we've already got our weight, 294, and we've got the vertical component of this, 64.3. Okay. We're going to add these two together to find our total upward force. Okay. So we're doing 64.3. Forgot to put in the plus before I started moving up. Plus 294. Okay, so that gives us a total downward force of 358, which means that our normal force upward to counteract that would also be 358 newtons. Okay, so now when we're looking for our friction force, FF just equals mu times Fn. We have both of those. Our mu is 0.2, and our normal force, 358. Okay, so 0.2 times that 348. That ends up giving us a friction force of 71.7 newtons. Okay. Now, looking for the last bit on here. G, the net force on the mower. So let's look at all the forces on our object. We have got our friction force. We've got our normal force. We've got our weight. We've got the vertical component of our applied force, and we've got the horizontal component of our applied force. Okay, all of our vertical stuff, we know because this thing isn't moving into the ground, cancel out. Our normal force and our weight and our vertical component total end up canceling out. So what we're left with is the friction force and our horizontal applied force. Okay, both of which we have. Since this thing is going to be ultimately moving in the direction of our applied force, let's make this positive and our friction negative. All right, so F net is just going to be equal to our friction of negative 71.7 plus our applied horizontal force of 76.6. Here we go. All right, so I'm just going to multiply that by a -1, and then we're going to add it to 76.6, ending up with a net force of 4.94 newtons. That thing is not moving very fast, which is fine. But we do have our net force now. Okay, so that gets us through the entirety of that review for test 3. If you have questions or you feel that I've made an error along the way, it is certainly possible that I plugged something in wrong. But if you have any questions, make sure to send me those on Schoology, or if you are in person, ask them in class before the test. Test will be on Wednesday. See you guys later.